if we look into the length scale of uh, whatever length scales we chose, we had chosen this. We had made this particular choice. So in that particular choice, the length scale in the y direction we had chosen to be capital L. That is, we mean to say that the variation in velocity in the y direction happens over a length scale L. This is what we had assumed. But if this is L, I mean this diagram is obviously exaggerated. So it means that the effect of that the change in velocity in the y direction is also affected on the length scale of L. But obviously we know it is not true. What is true is the length is affected over a distance delta which is sufficiently smaller than the length of the plate. And this we know from experience and experiments, that this delta is much less than the length of the plate. That is the transverse coordinate. So the characteristic length scale in the y direction is much smaller than the characteristic length in the x direction. Let us now encode these facts. So let us rescale everything. So the characteristics, so let us write down the characteristic quantities. So for the x direction we have chosen it to be L. The velocity u velocity we have chosen it to be u infinity. Now the question is, what is the characteristic length in the y direction? So it has to be delta. And what is the characteristic velocity? So now we know that because the u velocity is being retarded inside the boundary layer, so there is a retardation. So there will be some y velocity also. It is directly following from continuity equation. Any retardation in this will lead to a positive increment in the y direction. But what is then the scale of the y velocity? That is unknown, and that we can find out easily. So if this is the characteristic quantity, then the dimensionless, so we had already chosen, actually we can directly do it. X bar was chosen to be x upon L and y bar was chosen to be y upon L. But if delta is to be the characteristic quantity, we will multiply and divide by delta. So this becomes y upon L, y upon delta times delta upon L. So this becomes y star times delta upon L. Okay, so delta upon L, let us call it epsilon. So we call epsilon as the, it's a small parameter. Okay, it's small parameter, and it is essentially like the aspect ratio of the entire physics. So it's delta, that is the boundary layer thickness upon the length of the plate. So whatever we had derived in the equations previous to this, we have to simply now replace y bar with this. And in this equation, y star is now an appropriate rescaling. And it is an appropriate rescaling because now y star will vary from 0 at the wall to a value of 1 at the edge of the boundary layer. So it means that y star is always order 1. Whereas if we had kept everything in terms of y bar, if we had kept everything in terms of y bar would have varied from 0 at the wall to y bar equal to delta upon L at the edge of the boundary layer. And delta by L is quite small. Okay. So y bar would not have been an order 1 variable. It would have been an order epsilon variable. I hope you recall from computer science classes or data structures and programming or programming and data structures classes in your first year what this order indicates. So if something is 0.01, we say it's order 10 to the power minus 2. If something is 0.04, also we say it's order 10 to the power minus 2. So it's like a big O notation that you have studied in programming and data structures. It's just to indicate the order of magnitude, nothing else. It's nothing complicated. Okay, so far we have obtained a rescaled version of the y coordinate. So the rescaled y coordinate, y star, will be the original dimensionless coordinate upon epsilon. What is the meaning of this? In order to obtain a rescaled coordinate, we have taken our original coordinate and divided by epsilon. What is the meaning of division by epsilon? It is because epsilon is a small number, you are essentially multiplying y bar with a large number. So essentially you are magnifying this. You are magnifying this coordinate. If I were to draw, so if this is 1 and this is 0, so y bar, so if I were to plot y bar in blue, so y bar goes from 0 at the plate to epsilon at the edge of the boundary layer. So it would be something like this. Okay, so this is the edge of the boundary. So this is y bar equal to epsilon upon L. But now if I use y star, let me plot it in red. Y star varies from 0 to 1. So it will be something like this. So we are able to magnify this portion. We are able to magnify this portion to cast it as an order 1 variable. So this is the magnified part. And we are able to capture all the variations that are happening inside the boundary layer through the rescaled variable y star. So now if it is rescaled as y star, let us look what it implies from the incompressibility condition. Incompressibility implies del u del x plus del v del y equal to 0, and the dimensionless form was del u bar del x bar plus del v bar del y bar is equal to 0. Let us rescale it with y star. So y star is y bar upon epsilon. So this remains the same because we are not rescaling u bar or x bar. The characteristic length in the x direction is still L. So nothing changes over here. So this remains the same. So now V bar, let us call it VC bar del V star. Okay, where V star is the original dimensionless velocity upon some rescaling factor. So we call it V bar C. This is some rescaling factor. And y bar is going to be y star times epsilon. So this is this. And y star, you will recall, is now an order 1. Y star is an order 1 variable. U bar is also an order 1 variable because U bar changes from 0 at the wall to 1 at the edge of the boundary layer. Now X also is a order 1 variable because it varies from 0 at the leading edge to 1 at the trailing edge. Okay. So U bar, X bar are all order 1. So this entire term becomes an order 1 expression. Now we have to ensure that this entire combination of terms is also order 1. And why is that? Because we want incompressibility to be identically satisfied. In order for incompressibility to be identically satisfied, if this term is order 1, then this term has to be necessarily order 1 as well with a opposite sign. That's it. So the magnitude of this entire term has to be order 1. We have y star which is order 1, no problem. Now we are aiming to rescale the v velocity with an aim to make v star also order 1. We want to make v star also order 1. The whole purpose of rescaling is to render all the variables order 1 so that no variable is very large or very small. We want to make all the variables order 1. That is, we are trying to isolate the effects. So if in a given equation you find something is very very large, then you know that that term is going to dominate. Okay, but there will be some region where V star will be dominant. So V star is order 1, so this entire thing becomes order 1. Hence, this entire thing has to also become order 1. So Vc bar upon epsilon is also order 1. So Vc bar can be chosen to be epsilon. If Vc bar is chosen to be epsilon, right, then V star will be equal to V bar upon epsilon. Okay, so it means that whatever small velocity V bar would be, in order for us to resolve the physics inside the boundary layer, we have to magnify that velocity with this parameter. We have to magnify the very small y velocity. The logic being, if there is a retardation in the u direction in a very small layer, there will be a small y velocity which will be coming out. But now in order to resolve the entire physics, I must rescale this y velocity by epsilon in order to get a variation of the y velocity being 0 at the wall to something which is order 1 at the edge of the boundary layer. With the help of this scaling, we will be able to resolve the equations into their dominant and non-dominant terms. So we have finally x bar is equal to x upon L, y star is equal to y bar upon epsilon, which is essentially y upon L times L upon delta, and this becomes y upon delta. So this makes sense. We have u bar equal to u by u infinity, which is fine. V bar is equal to v upon, rather, v bar upon epsilon, which is v upon u infinity times L upon delta. Okay, so you are magnifying the v velocity. Now with the help of this non-dimensionalization, we can recast the governing equations. So del u del y plus del u del x plus del v del y is automatically rescaled. So in fact, let us call everything as stars only in order to keep things consistent. The x momentum equation would be, so originally it was u bar del u bar by del x bar plus v bar del u bar del y bar is equal to minus del p bar del x bar plus mu by rho. So there is a 1 by rho over here. So all the rows have vanished. This was 1 upon re del 2 u bar del x bar 2 plus del 2 u bar del y bar 2. Let me just show it once again. So this is the expression. So now we have to convert it. So in order to convert it, u bar and x bar remain the same. Y star is essentially y bar upon epsilon. So u bar del x bar. So v bar is v bar upon epsilon. V star is v bar upon epsilon. So this becomes epsilon v star and del u bar del y, this is y bar, so this becomes y star. So y bar is, yeah, so minus del p bar del x bar plus 1 upon re del 2 u del x2 plus del 2u del y star 2 1 upon epsilon square. So this epsilon cancels out. So we have, so now because we are writing everything in terms of star, so u star del x star plus v star del u star del y star is equal to minus del p star del x star plus 1 upon re del 2 u star del x star 2 plus del 2 u star del y2 times y star 2 times epsilon square. Now the y momentum equation, that is the most important part. Let me copy it. Yeah. So this v star, if you want to convert, so this will become del v star del x bar. So there will be epsilon. So v will be epsilon v star. This will be del epsilon v star by del epsilon y star is equal to minus del p star upon, so del y, so this becomes this plus 1 by re, so this becomes epsilon times del 2 v star upon del x star 2 plus epsilon upon epsilon square del 2 v star upon del y star 2. So if we divide everything by epsilon, we have u star del v star upon del x star plus v star. So if we divide everything by epsilon, this epsilon also vanishes. Del v star del y star is equal to minus 1 upon epsilon square uh, del p star upon del y star plus 1 upon re. So this epsilon will cancel out. So it will be del 2 v star upon del x star 2 plus 1 upon epsilon square del 2 v star upon del y star. Now in the x momentum equation, what are the terms that we have? What are the orders of magnitudes? Okay, so let me just copy this part. Let us discuss the orders of magnitude. This particular term is order 1, this particular term is order 1, this is order 1. What about these terms? This particular term is 1 by Reynolds number, this particular term is 1 upon Reynolds number epsilon square. Now, if Reynolds number is quite large, but epsilon is quite small, okay? If Reynolds number is quite large, then this term, the order of magnitude of this term will be quite small. So this term can be neglected in comparison to this term. Okay, so if we compare the order of magnitude of this and the order of magnitude of this, the order of magnitude of this term is larger than the order of magnitude of this, because here we are multiplying Re with epsilon square. So if Re is 10 to the power 5 and epsilon is 10 to the power minus 2, so this term becomes 1 upon 10 and this term becomes 1 upon 10 to the power 5. So obviously this term dominates over this term. So if we approximate this equation, minus del p star upon del x star plus 1 upon re epsilon square del 2 u star upon del y star 2. Okay. Moreover, we cannot afford to lose any pressure gradient terms. So if we want, so because pressure cannot drop out of any equation, pressure has to be written in all equations. if the pressure drops out from a given equation because of some botched scaling, so it can drop out. If you are doing the scaling incorrectly, pressure can drop out. So your Gurney equations for velocity and pressure will be devoid of pressure. So that cannot happen. So pressure has to always stay as a parameter in whatever you do. Okay, pressure has to remain in the problem as an important parameter. So if this is order 1, and so so if this has to be order 1, then this particular term has to also become order 1. So Re epsilon square becomes order 1, because this term is the second derivative that we are looking for. So there are two things going on. First is pressure cannot vanish, and the second derivative of velocity cannot vanish, because that is what is giving us the no slip boundary condition. In the absence of no slip, we don't need to ensure any boundary condition. If the flow is ideal, then this viscous term drops off. Okay, so the viscous term has to be retained and the pressure term has to be retained. So if the viscous term has to be retained, then Re epsilon square has to be order 1. Okay, so this term will be order 1. The pre-multiplying factor has to be also order 1. If it has to be order 1, then we have Re epsilon square order 1, that is Re times delta square upon L square order 1, that is delta scales as L upon square root of Re. And this means that larger the Reynolds number, the thinner will be the boundary layer thickness. Okay, large Reynolds number means thin, and it goes as 1 upon square root of Reynolds number. And larger the plate, the thicker the boundary layer that we had drawn. The larger is the span of the plate, the thicker will be the boundary layer. Okay, so in this x momentum equation, we have seen that this particular term drops out in favor of this term. These terms are obviously order 1, these terms are remain, this term remain. So remain, remain and remain. So finally the Gurney equation in the x direction. So u star del u star del x star plus v star del u star del y star equal to minus del p star del x star plus del 2 u star by del y star 2. Once again, the logic behind keeping pressure and behind keeping pressure and this viscous term is the fact that pressure cannot drop out of an equation. Pressure is a very valuable variable in the proper functioning of this entire sets of equation, and the viscous term cannot vanish, because it is the viscous terms that we are trying to sort of resolve the physics in. Okay, the boundary layer theory, if your scaling is able to neglect viscosity again, then obviously your scaling is incorrect, because why else would you be doing the scaling? We are doing the scaling in order to resolve the viscous boundary layer near the wall. So this term has to exist. Actually both terms would have to exist. The logic is both these terms would have to exist, but this particular term is much smaller than in magnitude than this particular term. Hence only the y derivative exists. Okay. So in the next class we'll look into the simplification of the y momentum equation as well, and we'll see how to take all of this forward.